So thanks to us, and thanks everyone for waking up early. So today I'd like to talk to you about a project that actually started when I was at University College London a few years back. And I would ride the London Underground every day to work, and they did a great job of putting Wi-Fi data connectivity in the stations, but when it came time to go through the tunnels, we lost connectivity. And so I was, thinking about, we have more and more people living in cities these days, and the future is going to be, hundreds of people in these trains simultaneously watching videos, teleconferencing, video conferencing, all at the same time. And so I started to think about how could we increase the capacity of these wireless network serving users on the go, on their commute, and meet this huge capacity demand unprecedented capacity demand that we really haven't seen yet today, but which I believe is around the corner. And then the other kind of relevant use case would be self-driving cars. So once you are on your commute in a self-driving car, what will you be doing? You might be watching movies on the go. You might be teleconferencing again. And we're going to have this very high-speed mobility and simultaneous demand for a huge amount of wireless capacity from hundreds of users on a road at the same time, wanting all this rich content from the wireless network. So to kind of summarize that, we have more and more people and more mobility and unprecedented amounts of data consumption on the horizon. And so I'm wondering, what is the best way of scaling up the number of bits per second per hertz per dollar that a wireless network delivers? So Wi-Fi goes to town is kind of one point in the space that answers this question. So the project kind of started with two observations. The first observation is the commoditization of Wi-Fi. So just a couple of years ago, you could buy a system on a chip for a Wi-Fi access point that would give you most of the functionality of a Wi-Fi access point for $5. And tomorrow, that price will go down. The second point is if you look at the evolution of cellular networks, which also could provide a solution to mobility, high-speed mobility. But if you look at the evolution of cellular networks and you ask the network operators themselves, you ask the question, what is the single most important thing you've done to your network to increase capacity over the past 10 years? Yes, MIMO increases capacity. Yes, the higher order modulations increase capacity. But the single most important factor, according to the cellular network operators themselves, is that cell size itself. Smaller cells create more spatial reuse and drive capacity up and up. So that's the kind of the idea behind Wi-Fi goes to town. The idea is that we have an array of very cheap access points serving mobile users driving past those access points. And what kind of system design do we have to target so that we can hand over between these cells very, very quickly? So I call this the kind of the vehicular picocell regime, because these are essentially picocells. They're going to be 5 to 10 meters in diameter, and we're serving users at vehicular speeds, so 30 to even up to 60 miles per hour. Okay, so the overall architecture is, the user is going to be driving by these access points. They're going to be connected by a back-end controller. The controller is going to coordinate these access points and make everyone happy. So the system is fairly simple, but the details are what make this kind of challenging from a systems building perspective and a network systems perspective. First challenge is how do we get around the association process for Wi-Fi. So as you know, a Wi-Fi client comes along and it has to associate to an access point in order to talk to it. So that association also involves some security. So when a client approaches the Wi-Fi Ghost to Town array of access points, it associates with the first access point it hears, but then the controller, the access points in the controller, they cooperate to push that association state information into all of the other APs. So if you dive down inside one of the APs, what's happening is the host APD software that's running in the kernel part of that Linux AP is extracting the association information and sending it to its counterpart kernel drivers in the other APs and pushing that association state so that we have none of that association problems. Now let's talk about what happens on the uplink when clients are sending traffic to the APs. So this could be you uploading your video to the APs, or you could be streaming a Netflix movie, and you could be sending those TCP/ACKs back to the Netflix server. So uplink is very important. The benefit we get is we have this diversity, link diversity advantage when we use many, many APs. So when the client sends a packet to all those APs, if one of them doesn't receive that packet, the other APs can step in and forward that packet. All the packets on the uplink are going through that controller, and the controller can very easily deduplicate those uplink packets. So uplink is kind of the easy case. Now let's talk about the downlink. So here, we don't want to duplicate the traffic that's going to go down to the client. If we did, we would lose that spatial reuse advantage that I was talking about that's going to increase capacity, right? So we have to select one AP, at least to make a first attempt at delivering that downlink packet to the client. So the client's going to be driving by these series of access points, taking channel information from all the transmissions that it's overhearing from each of the access points. When the client receives a number of readings, it can compare those readings and then feedback information as to the best AP at some particular time that is going to deliver the packet. So Suha. Yes.
So what kind of backhaul do you want to
Sure. So the question was, what is the backhaul between the APs and the other parts of the network? And we want to make the backhaul between the APs as simple and as low cost as possible, right? The good news there is that wired Ethernet, if you look at the historical trend of wired Ethernet link speed versus wireless Wi-Fi link speeds, they're a couple of orders of magnitude greater consistently. And so cheap Ethernet daisy chain backhaul is very feasible.
That would be fine because you need delay guarantees and so on to be able to do all these exchanges, right?
Yeah, I'll get to that in a second. Yeah. Okay, so in fact, this is to your point. Yeah. So what makes this hard, right? What really makes this hard is that the wireless channel is so unpredictable, and we can see this experimentally. If we look at the signal strength, this is measured in decibels of signal-to-noise ratio of a car as it's driving by at 15 to 20 miles per hour past 3 APs. So I'm going to plot you the signal strength on the y-axis here. And there's a couple of things I want you to notice. The first is, as you might expect, we have this overall trend where signal strength to AP1 first increases, then AP2 first increases, then AP3. But notice the small scale fading, the rapid oscillation up and down that is actually greater than that overall large scale fading trend that I just mentioned. As a result, the AP that's best able to deliver a packet on the downlink to that particular client is not going to be a simple 1, 2, 3 succession as the client drives by in a car. At the boundaries, those oscillations are going to make the difference and make the best strategy for choosing the AP be one that rapidly switches back and forth, as you can see here on the slide, between the two APs. And what are the timescales involved? So this happens, practically speaking, at vehicular speeds. This happens at less than 20 milliseconds timescales. Now, if you think about Wi-Fi, back of the envelope packet time for Wi-Fi is 1 millisecond. So based on this data, I would say significant advantages for being able to adapt on a timescale of 20 packets or less. The problem with Wi-Fi, and really any wireless technology, is that packet buffering is going to inhibit this rapid adaptation. So I'll get to you in 1 second. Yeah. So in particular in Wi-Fi, so many packet buffering packet buffering happens at so many layers that all that buffering is going to inhibit the time it takes to adapt to the wireless channel. So at the kernel level in software, we have the MAC80211 subsystem buffering. We have the Wi-Fi device driver itself with another buffer. And then down at the hardware, we have a smaller but still significant amount of buffering in that hardware transmit queue. The result is that if you run naively through an access point, you're going to take 2,000 packets backlogged. An access point, that's going to require about 2 seconds to transmit. And that's going to be a problem. So why is it a problem? Well, why is this so important? So getting this right has a significant impact on the overall efficiency of the system and the overall speed of the system. So we really, really have to get this right. And to illustrate this, if you look at data as it's flowing on the air at 6 megabits per second, for example, that's the lowest Wi-Fi bit rate. If you look at that, the packet time is very long, relatively speaking. That increased airtime is actually going to decrease the aggregate throughput. If we switch to an access point, say AP2 here, that has a better signal-to-noise ratio, what that means is that AP can adapt its bit rate to send at a much faster rate, up to, in an old Wi-Fi spec, up to 54 megabits per second. So the airtime will shrink significantly, and the overall system throughput is going to increase significantly. But this assumes that we have the ability to instantly move packets around. And this is playing against the buffering it takes to do that. So in practice, and this gets to the question that you asked, Suhas, it takes time to move packets over the backhaul from one AP to another. So if the packets start at AP1 and the channel suddenly goes bad, serializing those packets over the Ethernet and sending them off to AP2 is going to result in all that wasted airtime counteracting the very reason we sent the packets to AP2 in the first place. So we need to find a better way. So what we do with Wi-Fi Goes to Town is we pre-buffer the packets at all nearby APs. So the controller now is receiving 4 packets. It's going to take those 4 packets and it's going to push them to all the APs in the vicinity of a client that could be candidates for APs to deliver that packet. At that point, we can make very rapid decisions. The first AP, for example, delivering the first 2 packets, and if we sense the channel has gone astray, we can have the controller send a very, very short control message to the first AP saying, stop sending those packets, and another very, very short control message from the first AP to the second, or the controller to the second. So many different kind of control arrangements are possible here. To have the second AP go ahead and begin transmitting where the first AP left off. And these control messages, once the packets are acknowledged by the client, these control messages are going to dequeue these delivered packets so that one and only one access point delivers the data at a time. Let me hold the questions till the end, but I'll hold that if you wish. Yeah. All right. So that's all fine and good, but what some of you may be wondering is about the frame aggregation process in recent Wi-Fi standards, starting from 802.11n, and how that kind of plays against what I've described so far. So, I've kind of told you a simplified version of what happens in Wi-Fi, and now let me tell you some more details of what really happens. So, recent Wi-Fi frame standards, they amortize, as many of you will know, they amortize the time it takes to acquire the medium with CSMA and set up physical layer data headers and all the header information, all that fixed time overheads, they become more and more significant in the face of faster and faster Wi-Fi bit rates. So the answer to that from recent Wi-Fi standards is to have aggregates where a single transmission consists of multiple frames in one data aggregate that in their sum amortize the medium acquisition performance overhead, for acquiring the wireless medium. So the way this works is the sender is going to run a protocol to manage all these frames in an aggregate, assigning them sequence numbers, and then running a selective retransmit protocol that resembles TCP, but it's actually happening at the link layer. And so we number all our packets, and we have a send window where the sender can go ahead and transmit an aggregate containing frames, and then the receiver will send what's called a block acknowledgement. And this block acknowledgement is telling the sender which of the sequence numbers, which frames, sequence numbers, were successfully received by the receiver. And just like TCP, when the sender receives a block acknowledgement, ACKing data on the left side of the sender window, it can go ahead and shift that sender window to the right and open up that window and send more data. So we want to keep these block acknowledgements being received and the data quickly flowing through the system. The problem is if you start to lose a block acknowledgement. So once you lose a block acknowledgement, the sender is going to have to go ahead and retransmit all that data. So the block acknowledgement is just as precious as the data itself. You don't want to have the aggregate throughput that you're getting just because you lost that block acknowledgement. And so now, Wi-Fi goes to town. The solution is we have a kind of a co-design between the selective retransmit protocol and our array of access points. So think back to the uplink. We said we have this tremendous advantage with diversity. So now data arrives at the client. The client sends a block acknowledgement on the uplink, and it may very well be that the AP that sent the data, in this case AP1, doesn't receive the block acknowledgement. But we have this diversity of APs, AP2 and AP3, both of whom may have actually received that block acknowledgement. And so what Wi-Fi Goes to Town does is something similar to the association forwarding that I talked about in the beginning. It forwards those block acknowledgements to the AP that's currently responsible for managing that selective retransmit protocol between the AP and the client, which is AP1 in this case. So AP2 received the block acknowledgement, forwards it to AP1, and AP1 can take that, insert it into its MAC 802.11 subsystem and Wi-Fi driver, and fix up its scoreboard of packets that were successfully received by the client, because indeed the packet was successfully received. All right, so that's most of the mechanism of the design of Wi-Fi Goes to Town. So now let me shift gears a bit and talk to you about our implementation and a first test bed that we deployed at Princeton. So the setup was an 8 AP roadside hotspot test bed. And what we did was we were in the computer science building at Princeton, and we were in my office and all my colleagues' offices, which they generously volunteered to help this study. And we were stood off at a distance of about 20 meters from the road that you see there on the map that we were driving along. And we used these directional antennas in each of the office windows. The beam width of each was about 20, 30 degrees. And so our cell size, essentially, you can imagine the antenna projecting a cell onto the road. And so the cell size was about 10, 20 meters. And we were driving by, overlapping, right, because each of the offices is about 5, 10 meters apart. And so we were overlapping those cells on the road, driving by in a car up to about 25, 30 miles per hour. Each of the access points was made up of a commodity Wi-Fi card and a Linksys router, a very cheap Linksys router, and those directional antennas. So here's a visualization of how it works. And so in blue, you can see the packets on the downlink, and they're going to be coming from there's 8 APs. There's 8 APs that are indicated by the white squares in each of the windows of the building. And then the blue packets on the downlink, notice that they're not coming from AP 1, 2, 3, 4, and so on. You can see many times that we're switching back and forth very rapidly between each of the APs. On the uplink, we have green packets, and those were successfully received by the APs, and the red packets are those that are dropped. So you see we have a lot of uplink loss, and that's where that forwarding mechanism can kick in and recover that loss. All All right, so some more performance evaluations. So we compare Wi-Fi goes to town, everything I've told you so far, against the best kind of aggregation of all the roaming techniques for Wi-Fi that we know about. So there are two standards or substandards for roaming that have gotten rolled into the latest Wi-Fi standards. One of them is called fast roaming, 802.11r. The idea is that you make before you break, and you associate with a new AP before you deassociate with a current AP. That's a good idea, especially if you're walking. It's essentially what we do, but we take it one step further with all the packet forwarding mechanisms. The other is 802.11k, assisted roaming. That's the idea that the AP is going to tell a client what other APs are nearby, so the client doesn't have to scan. So scanning is when the client powers down, it essentially powers this radio down for communications and starts scanning on different channels to find what APs are nearby, and that's horribly slow, right? So we're going to give our comparison scheme the benefit of not doing that. If you look at products, Wi-Fi products like Aruba, Cisco, all these enterprise Wi-Fi products, they too have a controller, and they are optimized for walking speed mobility. And so the essential kind of advantage of having a controller is you get to do this association pushing, and you don't have to reassociate every time you migrate an access point. And so we give our comparison scheme the advantage of that too. So our comparison scheme has all the advantages except all the kind of the innovations that I talked to you about. Okay, so I'm going to tell you about the end-to-end throughput gain. I'll break down a bit about where the improvement comes from, and I'll talk about a little bit about scaling up with a number of clients. Okay, so if we look at throughput versus driving speed, and we're stationary right now, and we compare Wi-Fi goes to town in the black curve with the enhanced strawman scheme I described in the red curves. If we're stationary, no advantage, no switching, mostly, and so we're getting the same amount of throughput. But if we start driving past the access points up to 20 miles per hour, quickly past walking speed of about 3 miles per hour, our throughput plummets because we are just moving too fast for the reassociations to keep up. Wi-Fi goes to town, maintains throughput, and results in a 2x throughput gain. So where does that improvement come from? So in the paper, you can read all about this in more detail. It was in SIGCOMM last year, and there we study exactly how did these access points choose various bit rates to transmit at, and what were those bit rates comparing the two schemes, and what was the impact of uplink path diversity. So today I'll focus on what was the impact of agile downlink AP switching. So if we look at agile switching in detail, we can ask the question, could we have switched a bit slower? And if we did, would we still maintain our performance benefit? So we did that. So we introduced a hysteresis where we limited the speed at which we could switch, in this case to 120 milliseconds, in another case to 80 milliseconds, in another case to 40 milliseconds. So we stick with that AP. And then if you look at the throughput that you get when you vary this hysteresis factor, you can see that there are significant gains to be had by reducing the hysteresis from 120 down to 80 milliseconds for the gray throughput curve you see there on the right side of the screen. And significant but less diminishing gains for 15 mile per hour speed if we further reduce the hysteresis down to 40 milliseconds. And so, you can see these switching decisions, on the order of 40 to 80 milliseconds, even at a modest speed of 15 miles per hour, are really critical for performance. So finally, let's look at multiple Wi-Fi ghost-to-town clients operating at the same time. And how does performance scale with number of clients served? So we drove mobile clients in the configurations you might anticipate on the road. So first, following each other, together driving past the array of access points, we're getting an edge of 67% throughput improvement. And then if we look at two clients parallel to each other, so they're likely being served by the same access point, we can see that Wi-Fi Ghost to Town is maintaining its throughput, and the comparison scheme is even worse in terms of throughput. So we're really stressing the spatial reuse here, where the clients are competing for wireless bandwidth. And finally, crossing clients are kind of behaving similar to clients that are traveling alone. So these clients are now traveling in opposite directions, and because they are overlapping in space, at very seldom, we can see that they are behaving similarly to a single client throughput. So that kind of tells us that these Picocell APs are really getting the benefits of spatial reuse when there are multiple clients on the go. And Wi-Fi Goes to Town is maintaining that throughput level with the single client throughput for these crossing cars driving by. All right, so for even more details, experimental details, I'll refer you to the paper, but I want to kind of close with discussion about next steps on this project that I'm pretty excited about, and some further details. So, I described to you today that 10 AP testbed that was on the Princeton campus, and since then, Princeton has expressed interest in actually rolling this out to users in their production Wi-Fi network, campus network. And so what we have in the works is an effort that's joint with Princeton's IT department to scale up the AP counts and deploy this again, either alongside a campus light rail line that is about 2 miles long and connects the Princeton campus to the mainline Eastern Corridor train system. That's a light rail line, or along one of the major campus roads that runs about half a mile in the same direction. And so, besides that larger deployment, we also have plans in the works to integrate this with the Eduroam Wi-Fi federated access control that UCLA and Princeton both use, that you're probably likely using right now, actually, so that when faculty or staff take the light rail line or drive by down this road, they'll automatically, their phones and their laptops will automatically jump onto Eduroam, and we'll be getting production traffic, on our deployment. So this is a joint effort with the IT department at Princeton. So, so I'd like to acknowledge support of the NSF and the Google Research Award for this work. The papers and the videos and everything I've talked about is publicly available at my group's website, the Princeton Advanced Wireless Systems or PAWS group website. URL is there. And then to accomplish this deployment, I'll do a bit of a job advertisement now. We're actually hiring a Linux kernel developer for wireless networking. The URL is available there, and the job description is available there to work with the CS department, my group, and Princeton's IT department in order to roll this out in a larger scale deployment. So with that, I'd like to thank you all for listening, and thank you for holding your questions to the end. And now I'll be happy to take those questions. And I'll close there.
So we have plenty of time for many questions. So, yes.
Thank you for the great talk. And I was wondering, how many antennas on the field spectrum can go
So we're thinking of either serving, the short answer is we don't know yet. We're thinking of either serving every user, directly to their cell phone antenna, or in the case of a light rail, perhaps fitting an antenna onto the top of the light rail car and using a repeater, as is common, to serve the users inside. So it really depends on the use case. Yes. Yes, yes. So the question was, if the user has many antennas in one user, for example, so my cell phone has 2 antennas, for example. You're wondering, what if how do we deal with that? And the answer is, in this case, you would actually want to look. It's a MIMO link, really, and you would want to look at the MIMO matrix between each of the APs, and this is future work. But it's feasible with the channel state information that APs give you. And so this is what I would consider a good, interesting, kind of low-hanging fruit piece of future work, indeed. Good question.
So I have a follow-up question. How do you compare your system with the distributed antenna system? Like
Yes.
Instead of like how 3 independent routers, you can have 1 router.
Yes.
You can have multiple chains that locate the antenna at that location.
Yes.
And
So the question was, how do we compare our system with a distributed antenna system? And the extension to that question is, how do we compare our system to what's called a leaky feeder antenna system, where you basically have a coax cable with holes cut along the length of the coax cable, running down the length of the tunnel or along the roadway. That's another type of DAS. The answer is these systems are expanding the cell size, essentially, of wireless coverage in order to do fewer handovers. And for low data rates, they will indeed make a very reliable connection to a user going very fast, because it's literally you're distributing the antenna, right? So they're good for low data rates, but we're taking, you can think of that as the opposite side of the spectrum of the design space, and we're taking the other side where we reduce the cell size, because fundamentally that's what increases capacity. So DAS is actually going to reduce the overall bits per second you can give to all the users, even though it does work very well and is very popular for small numbers of users. But that's a great question, and we spent time thinking about that. So let me move on to Mark.
Okay, quick question. You showed the railroad, yeah?
Yeah.
And the passengers access the Picocell's 5 on there. Now, in the compartment of the train, you may end up with 10 users in the middle,
Yeah.
accessing entirely the same Picocell. So, you could decrease proportionally, or there is a contention problem there that ideal scale with the number of
Yes. So I would say the initial experiments I showed you, right, on the left side here, I mean, this is two cars, but you could think of this as people at the left side where the two cars are following each other, right? You could think of this as two people in the different compartments of the same train. And so we have demonstrated, sorry, I was standing in front, this situation here, yeah. So we've demonstrated improvements for this limited case. We have not yet demonstrated scaling that up to 10 users at once, and that's where we're going next. Good question. Within milliseconds, right? So the question was, how do we so quickly switch? And we don't have to switch within microseconds, right? So, wireless, let's go back to fundamentals, right? So like wireless channel coherence time moving at vehicular speed is going to be on the order of 3 to 5 milliseconds, right? And so the pre-buffering is the secret, or the secret sauce, I suppose. So pre-buffering the packets and then sending very short control messages over the Ethernet will have the latency that we need. Okay. Yes. Yes. Well, the last part is, okay, so the question was, I send an acknowledgement and I wait for the act timeout, and if I don't receive it, I'm screwed. But actually, no, because of the way that the selective retrans, what's it called? The block acknowledgement scheme works for 802.11n. So you have a send, what saves us from that is you have a send window. So you can tolerate, just like TCP, you can tolerate some time where you don't yet receive the acknowledgement and keep sending from your send window, just like TCP, and you're good. And yes, the windows, we need to switch and recover before the window size expires, but that's no problem. Okay.
So the pre-buffering, I had a question too. You mentioned there's these different layers of buffering that occur.
Yeah.
What level should I think about using pre-buffering? All the way down to the bottom?
Yes. So we actually, so ideally it would be all the way down at the bottom, but that requires a level of control over the hardware that is, totally theoretically and from a systems building perspective feasible, but not practical given, closed hardware and closed software drivers for the hardware. It turns out that, 6 packets is 6 milliseconds, and so that's roughly on the scale of a coherence time. And so we're like, not too bad if we sacrifice that hardware or don't use that hardware control and do all the pre-buffering, all these mechanisms in the software Linux kernel layer. So it's kind of okay, but we wish we had that control over the hardware. Yes. In back? Yes. What's the fundamental reason behind why we're losing the block X? What's the fundamental reason? So they're going on the uplink, and I suppose I'm showing you every time So they get received by all the APs potentially. And so I'm showing you every time an AP fails to receive that block ACK. And why did that happen? Because the multipath fading kicked in, and the car drove into a null that destroyed that packet, a frequency null that destroyed that packet, and we were at a low SNR. And simultaneously, the wireless bitrate adaptation that the client was doing didn't react fast enough, right? So it was sending at, say, 24 megabits per second, and if it had sent at a lower rate, it would have been received, but it didn't. And we're happy it didn't because it takes more airtime. So really, it's multipath fading at the end of the day.
Yeah, I was wondering, this is Wi-Fi.
Yeah.
Would you extend it to LTE also? LTE femtocells?
Yes, I'm sure you could. So the question was, can you extend this to LTE femtocells? And in particular, I don't know LTE, to be honest, as so well to be able to answer that question in depth. But LTE does have some kind of buffering, and the TDMA scheduling is gonna make this difficult. And I want to make a kind of also a cost argument that the Wi-Fi's commoditization is going to make Wi-Fi a bit more suitable for driving down the cell size, because you really want hundreds of Wi-Fi access points, right? So you want to make this very cheap indeed. Another interesting comparison point is high-speed rail, where the speed of the train is 200 miles per hour plus, and the cell size is much bigger, but the speed of the train is so much faster. And so it's certain that cellular operators have looked at something like this. So one way of thinking about this effort is like, what would they do if instead for Wi-Fi? So. Yes. Yes, okay. So question was, all the APs are operating on the same channel, and what would we do if we had multiple channels? And the answer is, think back to spectral efficiency. Spectral efficiency is bits per second per hertz, okay? So the answer is, the advantage of operating on the same channel is you get to do this on every single orthogonal channel. So for Wi-Fi in the 2.4 band, there'll be 3 of them. In the 5 gigahertz band, there'll be more of them, right? So you can do this at the same time. And so you're maximizing the throughput of your network by repeating this in a non-interfering way on the other channels. So that, I would argue, is quite promising for maximizing the spectral efficiency of the entire network. Now, that's kind of the short answer to your question. A longer discussion might be, what if we put these APs on different channels and kind of tiled the frequencies, did a handover in frequency? This would be a lot more complex, and so it's certainly possible, but we went with the simplest thing essentially. So I would compare what you just said to this design running 3 times on orthogonal frequencies. And I would say that performance comparison there is kind of open. But it's interesting to think about. It's a good question. Yep. Okay, so pre-buffering, you need to deliver to a set of APs nearby. And so the way we do that is all the APs are measuring signal strength to and from the client, and it's pretty easy to kind of see, if we go back to that data, it's pretty easy to see that, you know, at, let's see if I can draw on the screen. You know, at this point in time, at this point in time on the right-hand side, AP1 is pretty much had it in terms of its likelihood of delivering packets to the client. And then soon after, it'll stop detecting packets, right? So I guess the answer is we can pretty quickly and reliably rule out APs that are candidates. And then we're left with like pre-buffering packets to say 5 or 10 nearby APs. And that's going to give us a huge amount of diversity, so we're pretty much good at that point. So yeah.
So I had a couple of questions, some of which I don't know how you can ask, but a couple of them I thought about. So one of the things that could be thought of in contrast to what you were saying about the collection is coordinated transmission. In other words, almost looking at these access points and distributed antennas, but not sending it out as is, but doing it.
Yes, yes.
Or do anything smarter than that.
Yes.
That would essentially, of course, would avoid what you said about the spectral leakage, and could potentially increase. But of course, that requires more coordination. Basically,
let me respond to that. Yeah. So the question was how would I compare Wi-Fi Goes to Town with essentially distributed MIMO? So distributed MIMO, all the APs have a common phase reference, right? That is going to increase the cost because now you have to run a phase synchronization algorithm, and essentially it's a cost argument. Distributed MIMO is going to work better than what I have here in terms of spectral efficiency for sure. What this is something very simple, and so this is essentially the argument. Yeah.
And the second question I had was, in a sense, the aspect that is may have addressed, but it's unclear, is related to the scaling of the number of users. One of the issues will be of interference and backup. If you're using the same spectrum, the way you try to do this is by backing off when you have kind of flashes of large amount of users. Would that eat into your case? And how for a small number of users you may not see that. Would that affect?
Absolutely, yeah. Okay, so the question was, for larger numbers of users, would interference between the users eat into the performance gains of the system? I would say, very good question. We are going to, as future work, we will evaluate that. But we have interference between the current experiments I've shown you do have interference between 2 and 3 users that is not hurting performance. And the reason that is because of the decreased cell size. And so when you decrease the cell size, you are limiting the interference from adjacent cells. But you're totally right that we should rigorously evaluate this, and that's the plan with the next deployment.
And finally, for the uplink, you can also think of the following, where when you're handing off, so you basically listen at different APs and then piece together the packets received. Is that something you've done? Or when you're going through
so we listen to the different packets and we recover individual packets. One of the Test of Time awardees yesterday, Alan Mew, had a system called MRD back in 2001 that did exactly what you're saying. It pieced together the different packets from different APs. What that kind of, and we could do that, at the expense of some complexity. We just chose not to for simplicity. It turns out that you get most of the gains by recovering whole packets when you're looking at diversity on the uplink.
Other questions?
Let me not stand in the way of coffee break. Thank you.